Hello and hi. Okay, now we are in data mining topic 3, that is data pre-processing. Okay, let us start. The objectives of this topic is to explain the need of data pre-processing, to understand the major tasks of data pre-processing that include data cleaning, data integration, data reduction, and also data transformation and data discretization. So I will summarize everything. Okay, so let us look at this scenario. Imagine that you are a manager at All Electronics. To analyze the company's data with respect to the sales at your branch, you carefully inspect the company's database and data warehouse, identifying and selecting the attributes or dimensions to be included in your analysis, such as items, price, and unit sold. You notice that several of the attributes for various tuples have no recorded value. Users of your database system have reported errors, unusual values, and inconsistencies in the data recorded for some transaction. So, as you know, the data might be incomplete, inaccurate, or noisy, and also inconsistent. Okay, in the data quality multidimensional measure, a well-accepted multidimensional view can include accuracy, whereas the data inaccurate or has noisy, that containing errors or outlier value that deviate from the expected, human errors or errors in data transmission. Okay, next is completeness. The data may be incomplete. The attributes of interest may not always be available, or the recording of the history or modifications to the data may have been overlooked. Okay, next is consistency. Incorrect data may also result from inconsistencies in naming conventions or data codes used, or inconsistent formats for input fields such as date. For example, you put it maybe in the data ID 1, the date is 1 January 2020. But the ID 2, the date is 1/1/2020. So inconsistent. Timeliness, the data is not updated in a timely fashion, has a negative impact on the data quality. Believability, that reflects how much the data are trusted by users. For example, the past errors, however, had caused many problems for users, so they no longer trust the data. Interpretability, that reflects how easy the data are understood. The data also use many accounting codes which one in department does not know how to interpret. So it's also the multidimensional measure. Okay, the data pre-processing is an important issue for data warehousing and data mining. In the real world, data tend to be incomplete, noisy, and inconsistent. The technique of the techniques of data pre-processing includes data cleaning, data integration, data transformation, and also data reduction. Okay, let us recall data mining as a step of knowledge discovery. Okay, so this is the cleaning and integration, selection and transformation. Okay, so this is the data mining model. So this evaluation and presentation, so it will give a knowledge to the user. Okay. Early step of data mining, data pre-processing, data discretization or representation, and data selection. Data mining is a handling incomplete data, noisy data, or uncertain data. In the data discretization or representation, it transforms data into suitable values for the mining algorithm to find patterns. In the data selection, select the suitable data for mining purposes. So this is the data pre-processing. As you can see, data cleaning happened here. It clean all the noise. Okay. Data integration, it integrate maybe between two database or three database into one data warehouse. Data transformation is transform the data maybe from the, for example, -2, we transform it to -0.02. And also data reduction, whereas this is the data, we have a lot of data, so we just take a part of it, so we reduce some of it. Okay, data cleaning. So as you can see, we can fill in missing value, we can smooth noisy data, we can identify outliers, and also correct data inconsistency. In the data integration, we can combine data from multiple sources to form a coherent data store. In the metadata, correlation analysis, data conflict detection, and resolution of semantic heterogeneity contribute towards smooth data integration. Okay, data transformation convert the data into appropriate forms for mining. For example, attribute data may be normalized to fall between a small range such as 0.0 to 1.0. So as I mentioned earlier, we transform from -2 to -0.02. Okay. Data reduction, data cube aggregation, dimension reduction, data compression, numericity reduction, and discretization used to obtain a reduced representation of the data while minimizing the loss of information content. So as I mentioned, we reduce the data. Okay, in the data cleaning, step for handling data that are incomplete, noisy, and inconsistent. Data in the real world is dirty. Why? Because it can be incomplete, there is lacking of attribute values, lacking certain attribute or of interest, or containing only aggregate data. For example, occupation, we have a missing data here. And then we have a noisy, containing noise, error, or outliers. For example, salary equals to -10. So it's an error because salary cannot be -10. Inconsistent, containing discrepancies in codes or names. For example, age equals to 42, birthday equals to 03/07/1997, or we call it as or for example, we rate it as 1, 2, 3, now rating to ABC, so discrepancy between duplicate records. Okay, incomplete or missing data. Data is not always available. For example, many tuples have no recorded value for several attributes, such as customer income in sales data. Missing data may be due to equipment malfunction, inconsistent with other recorded data, and thus delete. Data not entered due to misunderstanding. Certain data may not be considered important at the time of entry. Not register history or change of the data. The missing data may need to be inferred. Okay. So this is the example for incomplete or missing data. Okay, let us see. Okay, in a wage increase third year, and also cost of living adjustment. Okay, yeah, this is the example of incomplete or missing data. How to handle missing data? Firstly, we can ignore the tuple. Usually done when the class label is missing when doing classification, but it's not effective when the percent of missing value per attribute varies considerably. Okay. Fill in the missing value manually, as you can put your value by manual. So it's quite tedious and infeasible, right? Okay, or else you can fill it in automatically with a global constant, example unknown, a new class, and etc. The attribute mean, the attribute mean for all samples belonging to the same class, for example, matter. The most probable value, okay, inference based such as Bayesian formula or decision tree. Okay, so for the noisy data, what is noise? Noise is a random error or variance in a measured variables. To smooth out the data to remove the noise, method of handling noisy data, we have several methods. There is binning, regression, cluster analysis. Methods are similarly to data reduction. Okay, simple discretization method, that is a binning, equal with, or we call it as a distant partitioning. Divide the range into n intervals of equal size or uniform grid. If A and B are the lowest and the highest value of the attribute, the width of intervals will be W equals to B minus A slash N, whereas W is the width of interval, B is the highest value of the data minus the lowest value of the data, and then we divide by number of data. Okay. The most straightforward, but outliers may dominate presentation. Skew data is not handled well. That is for equal width. Okay. For equal depth, or we call it as a frequency partitioning, divides the range into n interval, each containing approximately same number of samples. It's a good for data scaling, and also can managing categorical attributes, but it can be tricky. Okay, so as mentioned here, also used in data reduction slide 54. You can review to slide 54. Okay, binning methods for data smoothing. First, sort data and partition into equal depth or frequency bins. Then one can smooth by bin means, smooth by bin median, smooth by bin boundaries, and etc. For example, sorted data for price in dollar. Okay, we have here. Okay, we have 4, 8, 9, 15, 21, 21, 24, 25, 26, 28, 29, and 34. Partition into equal frequency bins. So, as you can see, we divide it into 3 bins, bin 1, bin 2, and bin 3. So, this belongs to bin 1. Okay. This will belongs to bin 3, bin 2, okay, and this will belong to bin 3, okay. So as mentioned here, smoothing by bins means bin 1 number of 999, bin 2 the number of 23, 23, 23, and bin 3 is 29, 29, 29, 29. So I will show here. You can refer to the another video that I already make for you for easy understanding. Okay, and then for smoothing by bin boundaries also. Okay, for example, okay, we must put number 4 here as equal to here, number 4. We cannot change it. And also number 15, we cannot change it. So the value that can be changed is the value that are in between minimum and maximum value. So this type of value. So as you can see, egg is more egg is what we call 4 to 8 is just 4, 5, 6, 7, 8. Also we have 4, but 8 to 15 we have 8, 9, 10, 11, 12, 13, 14, 15. We have 7 here. So as you know, it more nearest to 4. That's why the number is 4 here. Okay, so this also will be explained in the other video. Smooth out boundaries. The minimum and maximum values in a given bins are identified as the bin boundaries. Each bin value is then replaced by the closest boundary value. So it's more close. Like I mentioned earlier, 8 is more close to 4. So that's why we use 4 here. The number is 4. Similarly to number 9, okay, it's more close to 4. That's why we put it 4 here. Okay. Okay, so for equal width or distance, suppose we have the following data. Okay, first of all, we need to sort 24 data samples in total. Okay, so we sort it first. Okay, value 1, value 2, value 3, value 4, value 5, value 6, value 7, and value 8 and value 9. And then we put it in the frequency. Okay, how frequent value ones appear. Okay, and then for the equal width or in the distance, so as you know, we use equal value. So the bucket must be equal. So we can divide it 1, 2, 3, 4, 5, 6, 7, 8, and 9. So if 9, we can divide it by 3. So value 1, 2, 3, 4, 5, 6, 7, 8, 9. That's why we here value 1 to 3. The frequency, we must add everything in value 1, 2, and 3. Same goes to the bucket 4, 5, 6, and also 7, 8, 9. Okay, please note that equal width, the width of each bucket range is the same. Okay, so this is the histogram. Okay, as you can refer, this is the histogram picture. Okay, equal frequency, or we call it as a equal depth. Suppose we have the following data. Create a 3-bucket histogram. Okay, so as you know, because we use it in the equal depth, so we have a value 1 until 9 and also the frequency. The equal depth histogram, okay, we must, for the first bucket is 1, 2, you have 2. And then for the second bucket, we have 3, 3, 4, 5 is a 3. Okay, let me show it. Okay, this is a 2. This is a 3. Okay, and 6 until 9, we have a 4. Right? 6, 7, 8, 9. Okay, so and also the frequency here. Okay, please note that equal frequency or equal depth, the number of data sample in each bucket is about the same. Okay. How to handle noisy data? So we can have a clustering. is an unsupervised method. Outliers may be detected by clustering, where similar values are organized into groups or clusters. For example, a 2D plot of customer data with respect to customer locations in a city, showing three clusters. Each cluster centroid is marked with a plus, representing the average point in space for that cluster. Where is the outliers? So as you can see here, maybe here is the outliers. Okay, this is the centroid. Okay, so the outliers is reside maybe between here. Okay, it is also used in data reduction in the slide 58. Okay, regression analysis. Regression analysis, a collective name for technique for the modeling and data analysis of numerical data consisting of value of a dependent variable, also called response variable or measurement, and one or more independent variable, okay, as known as explanatory variables or predictors. Also used in data reduction in the slide 54. Okay, you can always refer to slide 54. Linear regression involves finding the best line to fit two attributes or variables so that one attribute can be used to predict the other. Used for prediction, including forecasting of time series data, inference, hypothesis testing, and modeling of causal relationships. Regression and log linear models. Okay, we are still in data cleaning. Linear regression, data are modeled to fit a straight line, often use the least square method to fit the line. Okay, so as you can see, two parameters alpha and beta specify the line, and they are to be estimated by using the data at hand, using the least square criterion to the known value of y1, y2, x1, x2, etc., etc. Multiple regression allows a response variable y to be modeled as a linear function of multidimensional features vector. Many nonlinear functions can be transformed into the above. So, this is the mathematical expression, as you can see here. Log linear model approximates discrete multidimensional probability distribution. The multi-way table of joint probabilities is approximated by a product of lower order tables. So we use a probability of A, B, C, D. Okay. Data cleaning, still in data cleaning, inconsistent data can be corrected manually using external reference. Source of inconsistency maybe come from the error made at data entry, can be corrected using paper trace. Due to data integration, for example, an attribute can have different names in a different database. Okay, why is data cleaning? Okay, you can refer to this YouTube, to this video for clear understanding. Data integration. Okay, so the data integration. What is data integration? It combines data from multiple sources into a coherent data store. For example, data warehouse. The source may be include multiple database, data cubes, or flat files. Issues in data integration. Okay, we have several issues. There is a schema integration, maybe redundancy, and also detection and resolution of data value conflicts. Okay, schema integration, what's mean by that? Integrate metadata from different source. Entity identification problem. Identify real world entities from multiple data source. For example, A dot customer ID, okay, probably same as B dot customer number. So this is the problem. Okay, A dot customer ID and B use customer number. Okay, detecting and resolving data value conflicts for the same real world entity. Attribute values from different source are different. Okay, possible reasons: the different representation, different scales. For example, metric versus British unit. Okay, we have maybe in one database we use a metric. The the second database we use a British units. Handling redundancy in data integration. Redundant data occur often when integration of multiple database, object identification. The same attribute or object may have different names in a different database, as I mentioned earlier. Derivable data, one attribute may be a derived attribute in another table, for example, annual revenue. Okay, and then we also have a redundant attributes may be able to be detected by correlation analysis and covariance analysis. Careful integration of the data from multiple sources may help reduce or avoid redundancies and inconsistencies and improve mining speed and also quality. Okay, correlation analysis in the nominal data. Given two attributes such analysis can measure how strongly one attribute implies to the other based on the available data. For nominal data, we use the chi-square test. The larger the chi-square value, the more likely the variables are related. For numeric attributes, use the correlation coefficient and covariance, both of which assess how one attribute's value vary with those of another. Okay, for example, if R of P and Q is more than 0, then P and Q are positively correlated. P's value increase as Q's. The higher, the stronger correlation. R of PQ is equals to 0 may be independent, or RPQ not more or less than 0 is a negatively correlated. Okay, visually evaluating correlation. So this is the visual scatter plot showing the similarity from -1 to 1. So this is from -1. Okay, and this is 1. Data transformation. Data are transformed or consolidates into forms appropriate for mining. A function that maps the entire set of value of a given attribute to a new set of replacement value. Okay, as each old value can be identified with one of the new value. It involves smoothing, aggregation, generalization, normalization, and also attribute construction. Data transformation, smoothing, okay, remove noise from the data. Aggregation, okay, what's meant by aggregation? The summarization or data cube construction. Generalization, the concept hierarchy climbing. Normalization, scale to fall within a small specified range. We can have a min-max normalization, z-score normalization, and also normalization by decimal scaling. Also, we have an attribute or feature construction. It's a new attributes constructed from the given ones. In the data transformation normalization, So min max normalization by using this mathematical okay, so this mathematical formula, for example, let income range 12,000 to 98,000, normalize to 0.0, 1.0, then 73,600 is mapped to where? Okay, so we have a v prime here, v dot min a max a. Okay, this is the mathematical formula for min max normalization. If you use z-score normalization, so that means okay, equals to 54,000, standard deviation equals to 16. Then we use this formula. Normalization by decimal scaling. Okay, where uh, v prime equals to v over 10j, where j is the smallest integer such that the maximum of v prime is a positive number modulus in a modulus, and it's not more than 1. Suppose that the recorded value of a range from negative 986 to 917. The maximum absolute value of a is 986. Find v prime for v equals to 900. Okay, let us see the. So this is the as you can see here, min max normalization. First of all, v. What is v? Okay, this is v. Okay, minus by mean of a. Okay, mean of a. What is the minimum value? This is the minimum value, right? Okay, divide by 98,000. Okay, maximum value of a minus by minimum value of a is 12,000. Okay, so we have a new maximum value of a. So new normalization is 1.0. So 1.0. Okay, and then minus by new minimum value of a is 0.0. Okay, plus new minimum value of a. So plus by 0. So it will become 0.716. Okay, for z-score normalization, as you can see, that mean u equals to 54,000. Okay, standard deviation is 16,000. Then we use a v. Okay, so v is still here. This is the value of v minus, okay, the mean of a. Mean of a is 54,000 divided by standard deviation of a, that is 16,000, equals to 1.225. Okay, so oops, sorry. Another normalization by decimal scaling. As you can see here, the v, where j is the smallest integer. Okay, so v is 73, right? Okay, so we will divide by 10. J equals to 3, so it will become 10 power of 3. So it will give this answer 0.9. Okay, it's quite tricky, and you can always check at my other video. I will show you the how step-by-step calculation. Okay, data transformation or feature extraction. So as you can see, we want to extract the data. Output from the RGB camera is the left, preprocessed depth center, and set of labels right for the image. So this is the living room, I think. Okay, so from this picture we extract until here. Okay, data reduction. The goal of data reduction is to obtain a reduced representation of the data set that is much smaller in volume but closely maintains the integrity of the original data. Mining on the reduced data set should be more efficient yet produce the same analytical result. Why? Okay. For example, a database or data warehouse may store terabytes of data. So the complex data analysis may take a very long time to run on the complete data set. That's why we must use a data reduction. Okay, we have several data reduction strategies. That is one, data cube aggregation, attribute subset selection, or data compression. Okay, we have a numericity reduction and also discretization and concept hierarchy generation. Data cube aggregation. So the lowest level of data cube, the aggregate data for an individual entity of interest. For example, data for quarterly sales are aggregate to annually sales. Okay, the resulting data is smaller in volume without loss of information necessary for the analysis task. Multiple level of aggregation in data cubes further reduce the size of data to deal with. Okay, we give a multiple level of aggregation in data cubes, or we also can use a reference appropriate levels. Use the smallest representation which is enough to solve the task. Okay, so this is the example for the year 1997, 1998, and 1999. Okay, so maybe the annual sales. Okay, the sales of 1997 is 1 million plus. Okay, so we use that. Okay, so we move to next, attribute subset selection. To find a minimum set of attributes such that the resulting probability distribution of the data classes is as close as possible to the original distribution obtained using all attributes. Why we use FSS? Why feature subset selection? Okay, because data set for analysis may contain hundreds of attributes that may be irrelevant to the data mining task or redundant. So please note in mind that we are still in the data reduction. Okay, we want to reduce the data. Okay, feature subset selection reduce the data set size by removing such attributes among them. Okay, the method include forward selection and also best selection. Stepwise backward elimination in the attribute subset selection. It starts with the full set of attribute. At each step, it removes the worst attribute remaining in the set. Okay. Note that the combination of forward selection and backward elimination, the procedure combines and select the best attribute and remove the worst from among the remaining attributes. Okay, so we also can have a decision tree induction and also redux computation by RST, rough set theory. Selection of attributes are identified by the concept of discriminability relations of classes in the dataset. Redundant versus irrelevant. Okay, so redundant attributes duplicate much or all of the information contained in one or more other attribute. For example, purchase price of a product and the amount of sales tax paid. Irrelevant attribute contain no information that is used for the data mining task at hand. For example, student's ID is often irrelevant to the data to the task of predicting students' GPA. Okay. Data compression, apply data encoding or transformation to obtain a reduced or compressed representation of the original data. If the original data can be reconstructed from the compressed data without any loss of information, or we call it as a lossless or no loss of information. If reconstruct only an approximation of the original data, we call it as a lossy. Two methods of data compression, this is a wavelet transforms and also principal component analysis. Okay. In data compression, okay, wavelet transform, a linear signal processing technique that when applied to a data vector D, transform it to a numerically different vector D of wavelet coefficient. Data are transformed to preserve relative distance between objects at different levels of resolution, usually used for image compression. Okay, so as you know, this is a data compression. Or we use the principal component analysis (PCA). Find a projection that captures the largest amount of variation in data. The original data are projected onto a much smaller space, resulting in dimensionality reduction. Unlike FSS, that reduce the attribute size by retaining the initial set of attribute, PCA, Principal Component Analysis, combines the essence of attributes by creating an alternative, smaller set of attributes. Numericity reduction. Numericity reduction technique can be applied to reduce the data volume by choosing alternative in a smaller form of data representation. Okay, so we can use a parametric methods. Assume that the data fit some models, estimate the model parameters, stores only the parameters, and discard the data except possible outlier. Log linear models obtain value at the point in MD space as the product on appropriate marginal subspace. Okay, or you can use a non-parametric method. What is non-parametric method? Do not assume models. Okay, so it happen in a major families such as in the histogram, clustering, and sampling. Techniques: check previous selection in data cleaning. Okay, so the techniques of numericity reduction, we can have a regression and log linear models in slide 22. You can have a histogram, clustering, and also sampling. Okay, what is histogram? So we can have a equal width. The width of each bucket range is the same. Or we can have a equal frequency, or we call it as a equal depth. The number of data sample in each bucket is about the same. Okay, or you can always refer to slide 17, that is binning. Okay, clustering. in the numericity reduction, partition data set into clusters and one can store cluster representation only, can have hierarchical clustering and be stored in multidimensional index tree structure. There are many choices of clustering definitions and clustering algorithms, further detailed in chapter 8. Okay, we also have a sampling. What is sampling? It allows a mining algorithm to run in complexity that is potentially sublinear to the size of the data. Choose a representative subset of the data. Okay, the simple random sampling may have very poor performance in the presence of skew. Develop adaptive sampling method. Okay, we can have a stratified sampling. Okay, in the stratified sampling, approximate the percentage of each class or subpopulation of interest in the overall database. Used in conjunction with skewed data. We also can have this is a type of sampling, simple random sampling (SRS). There is an equal probability of selecting any particular items. Sampling without replacement, or we call as a SRSWOR, sampling without replacement. As each item is selected, it is removed from the population. Okay. We can also the type of sampling with a replacement, or we call it as a SRSWR. Objects are not removed from the population as they are selected for the samples. So if sampling without replacement, WOR, as if each item is selected, then it will remove. But sampling with replacement, objects are not removed from the population as they are selected for the samples. In sampling with replacement, the same object can be picked up more than once. Okay, we also have a stratified sampling, that is to split the data into several partitions, then draw random samples from each partition. So this is the example of sampling. This is the raw data. Okay, so this is a stratified sampling. This is a cluster sampling. Okay, the stratified samples according to age. Okay, please note that out of 2 data are taken from each youth, 4 from middle age, and 1 from senior. Okay, so as you can see, the youth. Okay, here we have a 338, T38, T 391. So this one we take out. Okay, 4 from middle age. So from this data, okay, so become this data, and then 1 from senior. So we just take data T69 and we take out data T284. Hierarchical reduction. Use multi-resolution structure with different degrees of reduction. Hierarchical clustering is often performed but tends to define partitions of dataset rather than clusters. Parametric methods are usually not amenable to hierarchical representation. Hierarchical aggregation is an index tree hierarchically divides a dataset into partition by value range of some attributes. Each partition can be considered as a bucket. Thus, an index tree with aggregates stored at each node is a hierarchical histogram. Discretization and concept hierarchy. Discretization reduce the number of value for a given continuous attribute by dividing the range of the attribute into intervals. Intervals label can then be used to replace actual data value. Supervised versus unsupervised. Okay, so the supervised discretization process use class information. Unsupervised discretization process does not use class information. So by using a technique binning for unsupervised and entropy-based discretization for supervised. Okay, concept hierarchies. Okay, the concept of hierarchies is to reduce the data by collecting and replacing low-level concepts such as numeric value for the attribute age by higher-level concepts such as young, middle age, or senior. Automatic generation of concept hierarchies for numeric data. Okay, we have binning, histogram analysis, and also cluster analysis. We have entropy-based discretization, and we have a segmentation by natural partitioning. For categorical data, concept hierarchies may be generated based on the number of distinct value of the attributes defining hierarchies. Okay, concept hierarchy generation. Many techniques can be applied recursively in order to provide a hierarchical partitioning of the attributes. This is the concept of hierarchy. Useful for mining at the multiple level of abstraction. Can be automatically formed for both numeric and nominal data. For numeric data, use discretization method shown. Concept hierarchy, the generation methods for numeric data. Okay, so as you can see here, we use the data. Okay, this is a concept hierarchy for attribute price. So maybe the price is 450. So it's here. So it goes to here, right? So this is the concept of hierarchy. So the highest hierarchy is from 0 to 1000. So we divide it into the second rank and also third rank. Concept hierarchy generation methods for nominal data. Specification of a partial or total ordering of attributes explicitly at the schema level by users or expert. For example, street, city, state, country. Okay. Specification of a hierarchy for a set of value by explicit data grouping. Okay, for example, Urbana, Champaign, Chicago is a Illinois. Okay, Illinois. So, okay, we also have a specification of only a partial set of attributes. For example, only street and street, then city, not others. Automatic generation of hierarchies or attribute levels by the analysis of the number of distinct value. For example, for a set of attributes, street, city, state, and also country. This is the concept hierarchy generation method for nominal data. Automatic concept hierarchy generation. Some concept hierarchies can be automatically generated based on the analysis of the number of distinct value per attribute in the given dataset, but must consider the semantic of those attributes and relation among them. The attribute with the most distinct value is placed at the lowest level of the hierarchy. So you can see most distinct value. This is a most distinct value placed the lowest level of hierarchy. Okay. So this is in the Weka Explorer. Okay, so for the summary, data preparation is a big issue for both data warehousing and data mining. Data preparation includes data cleaning, data integration, data transformation, data reduction, and also feature selection. A lot of methods have been developed, but still an active research area. Okay, so that's all for today in the topic 3, data mining, data preprocessing. Thank you.